Okay, so we can now start the second talk of the afternoon session. So I'm happy to invite Professor Scott Sheffield from MIT. He will speak about random surfaces in Yang mills. Thank you.
All good? Okay. So today I will discuss random surfaces and Yang mills. So first, just let me mention for a couple of people in the audience here. So let's see. So I'll mention that Sharav Chatterjee, is he here? Yes, he's here, yeah. So he has this paper called Yang mills for probabilists. You can see it's dedicated to Raghu Varadhan, who just recently spoke on his 75th birthday. I don't know if any of you know how long ago that was, but in the relatively recent past, started working on this. And also, you know, if you're not a probabilist, he also has a talk, Yang mills for mathematicians, describing, and if you're not a mathematician, I don't know, do you have another talk for humans, maybe? But this is, and you know, I want to say that part of what motivated us getting into this talk was trying to understand some of the things that Sharav has written, and as well as things that were written in the more representation theory side by McGee and Puder and others, and seeing if we could combine and reconcile some of these points of view and maybe understand them from different perspectives as well. On the random surface side, I want to mention that if you go to my website, I have a bunch of things from like my ICM talk on random surfaces this year, and there's some notes from that really describe in a lot of detail this theory of random surfaces that we've been developing over the last 10 or 20 years. And this talk will be kind of about connections between this whole Yang mills theory as developed by Sharav and many others over the years, and this random surface theory that we've been working on. So let's get back to this story. So big puzzle in Yang mills. So Yang mills basically, lattice Yang mills assigns a random n by n matrix from some compact Lie group, like UN say, to every directed edge of a d-dimensional lattice. So we see here each little box has a matrix in it that comes from some particular, well in this case it's a discrete group, just so I could write it in nicely. And so you have a nice little matrix for every edge. And the rule is that if you reverse the direction of the edge, you replace the matrix by its inverse. So this edge goes the opposite direction from this edge here, so the matrix corresponding to this edge going this direction is the inverse of the one corresponding to the edge going this direction. Okay, so that's just a consistency requirement. And one way to construct a configuration like this randomly is to use IID Haar measure. So that'd be like choosing a uniformly random element from for each directed edge for one direction, and the other direction is just the inverse of that. But then you add a weighting that makes the product of directed edges around any unit square want to be close to the identity. Okay, so remember an Ising model, you know, you would assign spins to every vertex, and you want to make nearby spins the same. And here, well, you assign a random matrix to every directed edge, but you want to make, when you multiply the matrices around a square, you get something close to the identity. One way to do that is to weight by the exponential of a constant beta times the sum of the real parts of the plaquette traces. So for every square, we call it a plaquette. If you multiply the matrices around that plaquette and take the real part of its trace, well, within any compact Lie group, you know, its eigenvalues, they're all, you know, complex things with modulus 1, right? And so the real part we maximized when they're all equal to 1. It's the real part of the trace we maximize when all the eigenvalues are equal. So it's maximized when you get the identity. And so if you weight by e to this, then you're biasing towards things where the product around every matrix is close to the identity. Okay, and this, you know, sometimes they call this configuration a discrete connection. So in differential geometry, a connection is like a mode of parallel transport. So if I imagine I have a tangent space to a surface, as I move along, the tangent space moves. I do some sort of operation on the tangent space. And if it's a flat surface, then when you go around any loop, you come back to the same direction. But if you're, say, on a curved surface like the Earth, if I start here, I go up with parallel transport down this way and back this way. I've done a 90-degree turn over that period. And so that's a non-flat surface. So somehow this is weighting towards surfaces that are close to being flat. And well, in this my visual example here, I'm looking at the tangent space being rotated. But in principle, I could have any compact group and just talk about as I move along a trajectory, somehow in the continuum, I would be integrating some, I'd have some Lie algebra valued vector flow sort of. I'd be integrating against that. So that's what we would call a continuum connection. But here in the discrete level, if I give you any path on the lattice, you can multiply all the matrices in that path, and that would be sort of the matrix that corresponds to that path. What's the change you get when you follow that path? Okay, so that's the story. So Wilson loop is just the product of the matrices around any directed cycle, and we can compute the expected trace of that. That's the natural quantity that you're interested in, and so the Yang-Mills problem, roughly speaking, say the one that you get $1 million if you solve, is to construct and understand some basic properties of the continuum version of this. So there should be some sort of a limiting version of this, and you want to kind of show that such an object exists and understand some of its basic properties. Okay, so just notation, this is the same as in Shurov's paper. I can have a path which is a sequence of edges. A cycle will be a cyclic equivalence class of paths, so I can draw a path, but then make it reroute it, put the root somewhere else, and that'll be an equivalent path. So instead of E1 through En, I could do E3 to En and then put E1, E2 at the end. That's an equivalent path. And a string is a collection of loops. And a plaquette is a nice loop that just goes around a single square. And if I give a matrix Q P for a path, this is QE will be the matrix corresponding to a directed edge E, and QP for a path will just be the product of the matrices along that path. Maybe abusing notation a little bit, if L is a loop, then even though QL is only defined up to conjugation, the trace of QL is uniquely defined because the trace is a conjugation invariant thing. Okay. And any questions about that? Just setup notation.
So the allies in the string have nothing to do with each other. They could just arbitrary loops. For a string.
These loops? Yeah, this could be any collection of loops for now. Yeah. Well, okay. I mean, just because I'm saying trace of QL, but it's the trace of something that doesn't exist. Because QL is only defined modulo conjugation. But, okay, so if you insist on every piece of your phrase making sense separately, then you could say it's cheating. But trace of QL is a reasonable thing to describe. Okay. I could give it a different letter, but. So the Clay Institute famously promised to give $1 million to anyone who could construct a continuum version of Yang-Mills and explain some of its basic properties. Something they call the mass gap was one of these properties. It's important to solve this problem quickly because the prize amount is not adjusted for inflation. So really it's decreasing in value every year. You think of lattice Yang-Mills as a simple statistical physics model. It's like the Ising model, we want to understand something about the limiting model obtained when the mesh size tends to 0. And we want to give some sort of credible construction of the continuum limit, even if we can't prove right away that the lattice model converges to that. So for people who know this story, Oded Schramm thought about Ising model interfaces. So Ising model, remember, is this model where you have a bunch of plus and minus spins. And sometimes, depending on the lattice, you can find a curve that sort of separates a plus region from a minus region. And he thought, SLE would be, these particular random fractal curves would be a natural sort of scaling limit. If I took a really fine mesh and I had plus on one side and minus on the other side, and there was some sort of interface between plus and minus, that maybe this would be one of these fractal curves in the limit that he called SLE curves. But the thing is, he defined these curves, these SLE curves, long before it was proved by Smirnov and others that these curves actually converge to SLE in the limit. So somehow the construction of the limiting object came before we had the proof that discrete models converge to that. And these were, a couple Fields medals for this. These were kind of famous results when they achieved them. Polyakov and others constructed Liouville quantum gravity random surfaces, and these are continuum random surfaces, and they were motivated by these discrete random surfaces. But it was only much later that we could prove that these discrete random surfaces converge to the continuum random surfaces. Okay, so if you don't know what Liouville quantum gravity is, it's just a kind of random surface that was motivated originally because it somehow came from a quantization of the Einstein equations in 2D. So somehow a toy version of quantizing gravity led to a certain type of random surface. It also came up in string theory. In all of these stories, the discrete models guided the intuition. So they can help us construct the continuum theory even in cases where the scaling limit results are not proved. And so I want to stress that if you want the $1 million, you don't actually have to prove that lattice Yang-Mills converges to the continuum theory. You just have to construct a credible continuum theory. Now, thinking about the big problem, there are different approaches to this. So you want to assign a random matrix or expected trace to each nice enough continuum-directed loop, perhaps in some generalized function sense in some limit. And there are various approaches to doing this. So let me just mention a few of these. So one is the SPDE approach, which is try to construct a dynamical version of continuum Yang-Mills theory, maybe on a torus, and show that it converges to a stationary law in some large time limit. So you take the initial value to be what we call a Gaussian free field connection that is somehow believed to look correct at small scales. And then you hope that the other scales mix over time. And this is something that Martin Heyer, Hao Shen, Sky Cao, Bjorn Brinkman, Saurav Chatterjee, who's here, various other people have worked on aspects of this. And this is somehow pretty well understood now in 2 dimensions. There's been significant progress in 3 dimensions, that they're able to at least show this dynamical process makes sense for a positive amount of time. And if they can't yet show that it makes sense for infinite time and that it converges to something well-defined. But 4D seems to be out of reach, as far as I know, using this approach. Another approach is, well, you could try to construct the continuum theory without first constructing a dynamics. So, for example, constructing these random surfaces, we still don't have a good natural description of the dynamics for the random surfaces that would correspond to just taking a pair of triangles and then rotating them. These random updates you could do on random surfaces. There should be a continuum version of that, and we don't know how to describe that rigorously. So you might think maybe dynamics are harder than just constructing the stationary object. We don't really know. But it could be that you could just start with the Gaussian connection and try to modify the field in some other way to make it roughly correct at some scales, and somehow take limits as the approximation improves. So this is another one of the things people have thought about. And this third approach is the lattice approach. So explore this lattice model, and maybe in terms of random surfaces, and try to use that to gain some insight into the continuum theory. And the lattice approach, this is the approach I'm going to be talking about today. This is also closely related to what Shirov did with, he was talking about string trajectories, if you've read his works on this. It boils, lattice Yang Mills, it boils down to understanding expected products of certain random matrix traces. Random surfaces we consider today will all be planar or higher genus maps that are embedded in or mapped into a d-dimensional space. So special embedded maps called edge plaquette embeddings will play a role in what I discussed today. And so let me just start by telling you a little bit about these core ideas, matrix traces, and embedded maps. Anyway, how many of you have heard the phrase random planar maps before? Planar maps? Okay, so this isn't in everyone's vocabulary. So I should maybe say a little bit about what that means, and then how these topics relate to each other. Okay, and there are a couple recent papers I'll be discussing on that. This first paper here treats matrix trace problems in continuum 2D Yang mills, and the second uses these techniques to talk about lattice Yang mills in higher dimensions. So these are the two papers that today's talk is based on. They're kind of long papers. It's about 220 pages between them. But if you have time this week to just quickly give them a nice read, they're both up on the archive, and I'm very happy to discuss. Okay, but let's get back to these stories. So random matrix traces. So the heart of the 2D Yang mills problem is the following random matrix question. So you consider a compact Lie group like UN or ON or SUN or SON. And I define a Brownian motion on the compact Lie group. And to show you what that looks like, I actually did a simulation. Here is a Brownian motion on a Lie group. So in this case, the Lie group is a set of rotations of R3, orthogonal rotations. So this is O3 is the Lie group. And you can see the element of the Lie group by looking at what the cube is mapped to when you apply that Lie group element to it. And you can see the cube is moving around randomly. And you can imagine implementing this by just picking one of the three axis directions and doing a tiny epsilon rotation in that direction, and then iterating that. And then as your epsilon goes to 0 and these things, you're going to get some kind of continuously varying surface, which is Brownian motion. Okay, so you can just kind of trust me, this limit makes sense. And it's not too hard to write down rigorously what this is. And this is Brownian motion on a Lie group. So I showed this to my daughter, and she said, "What have you done to make that cube so nervous?" And well, Brownian motion is what we've done. Okay, so going back here, you can define such a Brownian motion on any of these groups here, and you define the normalized real trace. So the little tr will be 1 over n times the real part of the sum of the diagonal elements of the matrix. It's the usual notion of trace, but this lowercase tr means that I've normalized by taking 1 over n, and I'm taking the real part. And so if the m is the identity, then tr of m is 1, and tr of minus m is -1. And so this tr of m is always between -1 and 1. It's large, meaning close to 1 if m is near the identity, and it is small, -1 if m is far from the identity. And so consider A1, A2 up to AK, where each AI is the value of an independent Lie group Brownian motion started at the identity and run for ti units of time. Okay, so just take these I have these Ti, T1 through Tk, and I run each one of these things for a random amount of time. So if the Ti's are small, then these things are all close to the identity. If the Ti's are large, then things get pretty mixed. These are all pretty close to Haar measure. Okay, and now here's a random matrix pretzel. Compute the expectation. So suppose W1 through Wm are words in the AI and the AI inverse. So for example, maybe W1 is equal to A1, A3, A2 inverse, A3 inverse, A2, A1, or something. That's a word in these matrices. So I can construct a word like that and take its trace. And then I can ask, what is the expected value of the product of a bunch of these traces? And so this is a random matrix puzzle. Compute this expectation in a nice way. Okay, and I like this puzzle because you can describe this without knowing anything about Yang-Mills. This is purely just a question about random matrices. And this very particular type of random matrix, the matrix you get by starting at the identity and running your Brownian motion for a particular amount of time. So for example, I could ask, what's the expectation of the little tr of A1, A2, A1 inverse in terms of T1 and T2? It'll depend on these parameters. What is that value? Give me a formula for that. And on a follow-up, you can ask, what happens in the limit as Ti goes to infinity and the AIs become Haar measure? Okay, so and a lot of work has been done on this. So Terry Levy did a whole bunch of work about what happens in the n goes to infinity limit for these objects and gave up some nice formulas for how these behave in n goes to infinity limit. McGee and Puder have a whole bunch of stories about what happens if you just take Haar measure. So imagine Ti is infinity. So these AIs come from Haar measure. What are the expected traces of words you get like this? And in the work that Chatterjee has done on this, Shurov and Jafarov, it also is in this framework. So in their framework, if you take their beta equal to 0, then that would correspond to just products of matrices like this. And they also were interested in particular in the n goes to infinity case. They have a nice surface. I mean, they have results for finite n, and they also have results for n goes to infinity. And so we kind of were trying to do a two-dimensional version of the story, so to extend and understand Levy's results in terms of random surfaces. And we were also reading these other two papers, and we realized that we also could apply some of our techniques, two-dimensional surface, to give maybe a different way of understanding these results of McGee, Puder, as well as Chatterjee and Jafarov. Our answer to the puzzle mainly uses Poisson point processes, planar maps, and Wick's formula, which is somewhat different from the previous versions that often used representation theory, Weingarten calculus, and Haar measure integration by parts. It's a somewhat different set of tools, although related. And taking limits, we obtain alternate proofs of these results mentioned above, as well as some generalizations. By the way, let me mention a little advertisement here. If T is small, the matrices are close to the identity, then the product of matrices, when I multiply two matrices, it's similar to adding matrices. So products become equal to sums. And we also have some recent work on matrix sum spectral analysis with Hari Narayanan and with Terry Tao. And so I kind of want to mention this, partly because Hari's here, well, partly because I want to just put in a plug for these papers we did recently. So these are about when you add two random matrices, what can you say about the eigenvalues of the sum of two random matrices? If I fix the eigenvalues of the original two matrices, what does that tell me about the eigenvalues of the sum? And so that's a kind of a natural question. And if you ask about the trace of the matrix, that's a particular statistic of the spectrum of the sum. And the trace of the square of the matrix is another statistic, or the trace of the cube of the matrix. You can kind of probe different things about this spectrum in terms of these traces. So somehow this is a different way of probing the problem, and there may be some interesting connections. Okay. So anyway, that's just a brief advertisement. If you want this talk without ads, you have to pay a little bit extra. So further warm-up, let's Yang-Mills related random surface puzzle. So consider a uniformly random planar triangulation with a fixed number of edges, and weight it by partition function for a 3D Gaussian free field. Well, okay, let me kind of tell you what I mean by this. So in that article about random surfaces that I described, often you want to have a discrete random surface, and you think of the discrete random surface as something you get by maybe gluing together a bunch of triangles. You take a bunch of triangles, each edge of one triangle is glued to the edge of another triangle. You do this in an orientation preserving way, and you get some sort of a funny surface. Maybe the number of vertices, triangles meeting at a vertex doesn't always have to be exactly 6. This is some sort of random surface. It's not really a flat surface. And so one of the simplest ways to make a random surface is to just say, I'm going to start with 100 triangles, look at all possible ways of gluing them together, and then sample uniformly from that. And if I want to be fancy, I can say sample uniformly conditioned on the outcome being maybe a connected, simply connected surface. So something that's topologically a sphere. And this would give me a random, what we call triangulation of this sphere, a random way of gluing triangles to make a topological sphere. So that's one thing you could do. But I could also say, well, maybe I don't just want a random surface. I want a random surface together with an embedding of that surface into some d-dimensional space. So maybe I have the surface, and also for every vertex, I want to give you a number that tells you where, how this thing is embedded in R3 or R2 or whatever. So maybe this goes to the point 317. This goes to the point 216. This goes to the point 4913 or something. And so every vertex here gets mapped to some point. And so you could think of saying, well, I want to choose a surface together with an embedding. And in order to do that, if you want to think of a random embedded surface, you want to think that you're choosing. If you just forget about the embedding, then you want to somehow weight each surface by the number of ways to embed it. So what do I mean, number of ways to embed it? Well, you could put a constraint and say that neighboring points have to map to close by points in the lattice, any points that differ by at most some amount. And so you could maybe put that little constraint there and then say, maybe depending on the surface, there are more or fewer ways to embed it. And there's a continuum version of this where you put you do what they call a Gaussian free field on this thing, which gives you a different value, and you have some sort of a weighting where you weight by e to the minus the distance squared over all of these guys, and somehow you're choosing a random surface where somehow you're choosing a weighted where sort of the probability density for that surface corresponds to the weight it's given. And you can do that in one dimension. And, think of this, you have a surface mapped to one dimension. And then you can, but if you want to map to 3 dimensions, you can just imagine that as 3 separate maps, each to 1 dimension. So they say if you want a random planar map embedded in d dimensions, you take the probability measure that gives you just a uniformly random triangulation, and then you weight it by the partition function of the Gaussian free field raised to the dth power. And it turns out that makes sense even when d is less than or equal to 1, or even when d is a non-integer. You don't have the embedding, but you can still talk about the planar map weighted by, whose law is weighted by this partition function of that power. So, and most of these Liouville quantum gravity surfaces, they correspond to d less than or equal to 1. But there's also some special stories for d between 1 and 25. 25 is this critical value for bosonic string theory. 25 or 26, depending how you look at it. Okay. So anyway, that's just storytelling. But if you want to construct one of these random triangulations embedded in R3, I'll give you a very straightforward way of doing it. Let's say I start with a triangulation like this. Let's take some, I don't know, some lattice triangulation. So imagine I've kind of triangulated this whole thing. And I'm going to kind of randomly update this thing in the following way. Well, one way I can update is I can pick a vertex and just reposition that vertex according to a Gaussian random variable whose expectation is the average value of the neighbors of that vertex. Okay, so it kind of wants to be near the neighbors, and I just randomly sample. But there's another thing I can do, which is to pick sort of an edge like this and say, erase that edge and put in the edge the other direction. Or maybe I think that I pick a square and then I randomly decide whether to swap the edge or leave it in the same place. And the probability of going to each of these two options will be proportional to e to the minus the length of that option. So it prefers to, minus the length squared, so it prefers to be kind of in the shorter direction, but occasionally, just by chance, it'll go to the longer direction. Okay, and if I do this at random, and just keep randomly doing this, I'll get a fluctuating surface. Okay, and I want to sort of probe what you guys think this surface is going to look like before I actually show you. How would you imagine this Glauber dynamics, where you randomly resample this thing or move edges? What do you think this is going to look like? So I'm going to have this start with a flat surface, or just a triangulation, and I'm going to kind of randomly mix up the triangles, and they're all going to be moving around, and points are going to be moving around. I'm going to get some fluctuating surface. Okay, it's going to stay simply connected, and the boundary will stay in the same place, but the surface is going wild. And the question is, in what way is the surface going wild? So everyone visualize what you think is going to happen, and I'm going to take a vote to see what you imagined. Okay, so how many of you imagined relatively small fluctuations about sort of an area minimizing equilibrium? Sort of a, anyone imagine that? A couple people? Okay, you can read ahead if you want to pick which your vote is. You have to vote, by the way. If you don't vote, you're kicked out. So you have to think of one of them. So second one, how many imagined kind of giant waves on a Brownian map-like fractal surface? You have some big fractal going up and down. You could surf on that. Okay, all right, vote that. How many of you imagined a single dancing tree larger than everything else? If you measure that. How many of you imagined an open field in which cannibalistic robot insects fight each other to the death? You imagined that? Okay, yeah. All right, well now we will see who is correct. So here's this surface when you get started. And at the beginning, it looks like the people who voted A were correct. It kind of stays roughly flat. But partly it's because it really hasn't had any time to do anything too wild yet. Oh, it's some sort of fluctuating random surface. But I do want to say that in 3 dimensions, there is a belief that if we didn't have the boundary constraint, the thing would ultimately look like a tree. And it would kind of look like you take a tree object and you imagine like a surface that sort of, well, I mean, it turns out that weighting by the number of, there's this matrix tree theorem that says the partition function for the Gaussian free field is sort of inversely proportional to like the number of spanning trees, or maybe the square root of that. Anyway, so the surfaces that have a lot of embeddings in R3 are the ones that have relatively few spanning trees. And the surfaces, if you look at what kind of graphs have few spanning trees, well, trees have very few spanning trees. If I give you a tree, that's a connected graph that only has one spanning tree. And so they sort of are expected to look more tree-like when you're embedded in a dimension as high as 3. But on the other hand, the tree will be randomly embedded. And so you think of it as sort of a continuum random tree randomly embedded. They call it sort of a branched polymer. And so when it's random embedded, it'll get kind of bunched up in some funny way. But let's see what happens here when I run this surface for longer. This will run much faster. And at the end, what you see is, in fact, cannibalistic robot insects fighting each other to the death. So what happens is each one of these is one of these kind of tree-like objects, but it's all folded together, because it's randomly mapped in. But it sort of wants to be a single tree. When two of them collide, one of them eats the other, and then they don't separate from each other again. So you can kind of see how they're gobbling each other up. And my guess is if you ran this for long enough, you would probably get just one big tree. But it might take a really, really long time for that to happen. Okay. Anyway, this was just for fun to give you a flavor of what these random surfaces might look like. You have some intuition for surfaces. Okay. Here's I mentioned there's another paper we recently posted about visualizing planar maps this year, but we'll say more about for that. Okay. Now there's another story about planar maps. So consider a pair, M phi, where phi is a planar or higher genus map, and psi is a graph homomorphism. I'm going to assume that the dual graph of M is bipartite, so there'll be two kinds of faces, blue and yellow. Now phi is going to map each yellow face of M isometrically onto a face of L. It will map each blue face of M onto a single edge of L. I'm going to call this an edge plaquette embedding, because each blue face maps to a single edge, and each yellow face maps to a single plaquette. Plaquette meaning a square in the lattice. And so here's a picture of kind of how this might happen. So on the top here, I have a grid, a 4x4 grid. This is just a particular example to illustrate. This is a 4x4 grid of blue squares. And each one of these blue squares is going to get mapped to one of these edges in this 4x4 grid of edges. Okay, so imagine each blue square will get collapsed into a single edge, whereas I go around this square, I'm just going up, down, one of these vertical edges. Up, down, up, down. So think of it as these yellow edges are made out of metal. They can't be collapsed, but the blue faces are made out of cloth. So they can fold up like an umbrella. And so all of these blue faces get folded up like umbrellas to these vertical lines. And then these yellow faces, there's a yellow face between every pair of blue faces. And that will get mapped to the yellow face here that is between those two corresponding vertical edges. And, each yellow face, connects to two of these white things. And one of them will correspond to the top, and one of them will correspond to the bottom. And so I put the red edges to indicate the one that goes to the top. So this is sort of a construction for how to fold this thing up. So fold all of these metal things up so that the red things come to the top, collapse the blue faces like umbrellas, and you can crumple this thing up to create this object. If you purchased this at IKEA and it came with instructions, you could figure out how to fold this up and produce this. Okay, now here, this is the same thing, except I've added this little extra gadget in the middle of each of these blue things here, which is some blue two-gons and then a yellow square, a yellow four-gon. And the way this is going to map, this maps in is each one of these yellow four-gons will map either to the top or the bottom of one of these empty regions here. So here's an example of a planar map, which is all yellow and blue. And I have folded this up, so each one of the yellow regions gets mapped to a square, and each one of the blue regions is folded up like an umbrella to one of the edges. Okay, and this is what we call an edge plaquette embedding. Now there are different ways of doing this, like, so morally speaking, a two-gon gets flattened to an edge. A four-gon, you can think of it as a yellow, blue, or green, or sorry, red, green vertices. So when you fold it up, these things will get mapped to one side, and the green things will get mapped to the other side. Then I glue these things together to this step, and then I squash it all to an edge. Or if I had three things, I first fold this thing up, so it's alternating between red, green, in a shape like this. I squash these edges together, and then I squash the whole thing up. Okay, so that's the procedure for folding these things up into edges. And so, in principle, I could have a blue octagon with 8 faces around it, and then this whole blue thing gets folded up like an umbrella into a single edge, and then these 8 things will all get mapped to different faces around this edge. Okay, this is what we call an edge plaquette embedding. It's a particular thing you can do. Here's another picture of this where you've got, if you imagine, first you only see where the yellow plaquettes are, then I have to decide what goes in between them. So maybe this is the blue face here. So the yellow faces are only connected to blue faces. So blue is sort of the glue between the yellow faces. So maybe I have this 6-gon in here. Maybe this is a 2-gon here between this and this. So these will be shrunk. This is the same point here and here. Maybe this is a 4-gon here. And then if I want to, I can unwrap this thing, spin this thing around and make it look orientable. And then I could glue a bunch of other stuff in the middle here. And then I can imagine mapping this back into this region and getting a map like this. Anyway, this is just to give you sort of a feel of what these things can look like, these edge plaquette embeddings. So this is an example. Here's the planar map, and here's how it gets mapped into this thing. And these various blue pieces will get mapped to different edges. Okay. Okay, so remember we had this notation here. The fundamental object we want is the expected product of these real part of these traces with respect to some measure, which is basically you take the product of hard measure for every edge, you multiply by this, z is just some constant, by this e to the n times beta, some constant times this sum of all these traces. And so this is our hard measure. And you can replace, by the way, it doesn't really have to be an exponential function. It could also be a real polynomial that's large near 1 and small but positive elsewhere in the interval between -1 and 1. So you can put there's exponential is convenient for some purposes, inconvenient for other purposes. You can decide whether you want to use a different polynomial instead. For example, you could take x goes to x to 100 times 1 plus x. If you think about that, that will be something that goes to 0 at -1 and is big at 1, and it will be bias you heavily towards things that are close to 1. Okay. Now we want an edge plaquette embedding model that is useful in Yang-Mills theory. And so we need to assign a weight to every face of L, depending on the number of plaquettes there, and every edge, depending on the number and type of blue faces that are there. And to do this, we'll use something called the Weingarten function, which is the inverse in the group ring of Qn SL of the function that takes sigma to n to the number of cycles of sigma. So sigma is a permutation. And so if I take a function on the thing that takes a permutation to n to the number of cycles of the permutation, that's a function on the permutation group. Right? And so, well, there's a group algebra, and I can, or a group ring, and I take the inverse in that group ring, and that gives me a different function. And that function is called the Weingarten function. Okay, so if you haven't heard of it before, it's just some relatively simple function that you get by starting with this n to the number of cycles and taking this inverse. One thing about this function is it depends only on the conjugacy class, so only on the cycle structure of sigma. So you can think of it as, if I order the cycles from biggest to smallest, that's a Young diagram. So I can think of the Weingarten function as being defined on Young diagrams. It's kind of not the simplest function to understand directly. So you can expand it in terms of characters of this symmetric group. But if you write it in that way, it's kind of complicated. So there's no general explicit formula for the irreducible characters of symmetric groups. And it looks like maybe this is kind of a complicated function, but at least in terms of the idea that it's the inverse of this simple function here, we have a good understanding of what this object is. Okay. All right, and then this theorem. So here we give you a first theorem here. When the gauge group is UN, the expected trace product is proportional to the sum of this product of WE times n to the minus 2g, where the sum is over all of the spanning edge plaquette embeddings with the given plaquette numbers, and G is the genus. This is where I imagine I fix the number of plaquettes of each type. So I tell you how many yellow plaquettes of each type you're going to have. And okay, then the expected product has this particular form. And there are variants of this story for other groups. Okay, so somehow in gauge theory, I can imagine that I start by having all these squares that I put in, and I'm weighting by the real part of the trace around that square. But then I additionally have a few big loops. I put in maybe a big loop like this, another big loop like this, and I want to know, what changes when I put in these big loops versus if I just had the small loops. And to understand that, I have to say, well, when the big loops are there, what's the expected product of all these traces compared to if the big loops weren't there? And when the big loops are there, it's going to be basically, I'm going to be summing over all the surfaces I can make by gluing in these blue faces, in between this, in some way, in between all these yellow faces, and using that to make a surface. So I just sum over all the possible ways of doing that with this particular weight, and voila, that is going to be the expected product of these matrices, of the traces of all these loops in the Yang-Mills theory. Okay, so I haven't given you any hint of how to prove this yet, but I'm telling you that there is this sort of miracle that if I want to compute these what we call Wilks loop expectations, this expected product of all these traces, it is equivalent to somehow counting surfaces, or this weighted counting of the surfaces. But there's this weight n to the minus 2g, so n is somehow this dimension of this group we have. So if it's un, sorry, this little n is the same as this big N here. So this is telling us that it really depends on what kind of n I put here. If n is just 1, if I'm taking U1, then I don't really care what the genus of the surface is. It's just sum over all the surfaces with this Weingarten weight. I'm ignoring the genus. But as n gets larger, I care about the genus more and more. And as n goes to infinity, these surfaces become simply connected. This is related to the string trajectories in say, that Shurov has talked about in his papers. So in that case, you have a string that is sort of evolving in time. You're gluing plaquettes to it. And then at some point, it vanishes. And this is somehow over time that the string trajectories trace out a surface. And somehow this is related to that. But I don't specify the particular trajectory by which the surface shrinks to zero. I just assign a particular weight to each overall surface. This is still a large sum, by the way. There are a lot of surfaces. But if the number of plaquettes wants to be small, the surface might approximate somehow a minimal surface. Maybe you get most of your contribution from surfaces with very few plaquettes. All right. And so in general, also there are a lot of symmetries that allow cancellation. So there are moves that change the sign but don't change the genus. And in 2 dimensions, what we find is there's a surface story where you can write these loops as sums over surfaces. And there's a way of doing it where you only have to consider flat surfaces. So surfaces that are locally somehow minimal area. And so somehow, that means that even though in this theorem we're summing over all surfaces, at least in 2 dimensions, it's only the flat minimal area surfaces that really matter. So you've got a big sum over all crazy surfaces that can go as far apart as they want. But from another way of looking at it, it's really only the flat surfaces that can contribute. And there could be many flat surfaces. If I have something like this, there could be like a ramification point that could be anywhere inside this smaller disk. So I can have a surface, I can position that point, and so there's still some interesting things in terms of how many places there are to place these points. There may be different combinatorial ways to construct the surface. So it's still kind of a non-trivial number if I give you a bunch of crazy loops like this and ask you what's the quantity for that. It may be kind of non-trivial to say what that is. But somehow this first paper was really saying you can write it in terms of surfaces, the surfaces are all flat. And the second paper is saying, well, if you look at the lattice point of view, you're writing it in some surfaces where they aren't all flat. But somehow in 2 dimensions, there should be some weird cancellation where only the flat ones matter in the end. Okay, so that's this story. And so somehow, you might think the battling insects cancel each other out maybe in high dimensions. Is there some reason that even though you're summing over lots of surfaces, maybe the ones that matter are the flat surfaces? We don't really have a great answer for what's happening in dimensions 3 and higher. But in 2 dimensions, we sort of, at some level, understand this story. By the way, McGee and Puder, they mentioned some other things about this of Weingarten function. And I just want to point out that they have some stories about what happens as this n parameter goes to infinity. And things are somehow, things become simpler in that case. These reduced to Catalan numbers, and somehow you don't have to. Somehow the weight is just like a product of weights corresponding to each type of plaquette. Squares get some weight. The 6 gons, 8 gons each get different weights, and it's not really as complicated as a measure that requires you to understand the whole Young tableau. It's just a different weight for each of the row lengths. So it becomes, kind of more of a classical planar map story in this n goes to infinity limit, I guess. Let me mention another story. By the way, I don't have any sort of clock here. I have no idea how I am on time. 5 minutes? Okay, so I should fix things up. So the various stories in Yang Mills, one is what they call gauge fixing. So if I give you any one of these crazy planar maps, there's a way to sort of reduce to the case where along a spanning tree you make everything equal to the identity. And there are just some kind of symmetries of the model that you can use to somehow reduce to that case. And change the gate choice, changes this thing by a conjugacy class. And because of this sort of this fact in 2 dimensions, I can gauge fix. My lattice is some square, I can gauge fix so that maybe this whole spiral thing, or maybe I can draw this a little better. I can have all the matrices be the identity along some big spiral like this. And then the only edges I have to understand are these edges. They're sort of like a ladder of edges, a spiral ladder that goes around like here. And then I can kind of check that, if this edge is free here, that it's sort of just Markovian. Each time I go from one edge to the next edge, I'm just doing sort of a random walk in this Lie group, taking some small step. And so the overall value at the end is just going to be this, in the fine mesh limit, it's just going to be like running Brownian motion on a Lie group for a time that depends on the area of this structure. This is only in 2D. So in 2D, we kind of understand very well the law of the product of matrices around a whole Wilson loop. And it's just given by this running a Brownian motion on a Lie group for amount of time that corresponds to the area of that group. And if I take some fancy loop like this, I get some crazy word in the matrices that correspond to each of the regions that the loop divides space into. So each one of these regions, there will be some Wilson loop around that, and I get some word in these guys. And so this is what we were understanding when we wrote the 2-dimensional paper. And so I want to mention here, well, let's see. First, let me say here, mention there's a whole bunch of people who've done work on the classical matrix map stories. So these stories about connecting planar maps to random surfaces, they go back all the way to the 70s. And I really don't have time to give you a great story about the history. But let me just mention that there is a lot of it. But in this 2-dimensional case, if we go back here to or let me get to the web browser. Oh, by the way, one more shout out here. This is Nishant Changoshia is also a co-author in the audience, who we did some work together with Catherine Wolfram on the 3D dimer model, which in some sense gives you a random divergence-free flow in the fine mesh limit. And the random divergence-free flow, we believe it's probably Gaussian in the limit and looks the same as the curvature of one of these Gaussian random connections in the Gaussian free field version of a random connection, which is somehow some small temperature limit for Yang Mills. So let me just toss that out there. But this paper by Terry Levy, he came up with some, at the very end of this long paper, he has a chart where he actually computed the Wilson loop expectations corresponding to a whole bunch of loops. And so see, say, for this loop here, so if they're all loops with at most 3 intersections, I guess. And so here there are regions which you call, say, S, T1, T2, T3. And then there's this particular expression. And this is going to be the Wilson loop expectation, and the n goes to infinity limit. And it depends on the areas of these 3 things. And so here it is as a function of those areas. Theta minus S over 2 minus T1. It's some weird function. And what we showed is that all of these quantities here, they somehow correspond to these sums over random surfaces that have this thing as the boundaries. And this T1 here, T3, they correspond to, you have room to place ramification points in these things. So a T1 area worth of places to put them. And what we also did in our paper, our first paper, is we generalized this story to finite n. So this is the n goes to infinity limit. But in our paper here, we were also able to do finite n versions of these things in Terry's chart. So I can show you what these look like here. Well, I don't know if you get anything from these formulas, except that, haha, we computed them. But it's something. They involved a lot of Cauchys and Cinches, and whereas the other ones were just exponentials. But you can see they all have some dependence on this big N, and if you take the N goes to infinity limit of this chart, you get the things in Terry-Levy's chart. And here, finally, this is the paper where we do the lattice work, and the key thing I want to mention here, is that the way we prove everything is really using what we call Wick's formula, which is just a formula for what's the expectation of a product of Gaussian random variables. And we take all this Brownian motion on a Lie group and we write it as, imagine a product. I can take the identity plus a Gaussian element of the Lie algebra, of a tiny Gaussian element of the Lie algebra. That's sort of approximating Brownian motion 1 for a very small amount of time. That I can multiply a bunch of these things together. And sort of in the limit is that as the small perturbations become small, I really recover exactly this Brownian motion on the Lie group. But with this approximation, everything is Gaussian. And so I can just apply Wick's formula using this classical matrix expansion that lets me connect these things to random planar maps. I do the story that way, and then I somehow take the limit as these sizes get small, and then take the limit as the Brownian motion goes to infinity, and I somehow recover all of these other stories just by starting with Wick's formula and Gaussians. And the representation theory, meaning the Weingarten function, it sort of comes in at the very end of the story. So some of the other approaches, they start with the representation theory from the beginning, whereas for us, we only start with Wick's formula and Gaussians and a whole bunch of work. I mean, it's still 200 pages. We have to do a lot to do all the different kinds of groups and everything. But somehow the representation theory is the last step rather than the first. Anyhow, that's it for today. Happy to take questions.